Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 377, combination sum 4. This problem focuses on generating combinations that sum up to a target value, using dynamic programming or other strategies. Let's dive in and explore the problem and its various solutions step by step. In this problem, you are given an array of distinct positive integers called nums, and a target integer called target. The task is to calculate the total number of possible combinations of elements from the nums array that add up to exactly the value of target. The order of the numbers in each combination matters, which means that combinations like 1, 2, and 2, 1 are counted as two separate results. It's also important to note that the result will always fit within a 32-bit integer, so you won't have to worry about overflow. The input consists of constraints where the length of nums can range from 1 to 200, and each number in nums is between 1 and 1000. The target value will be a positive integer, ranging from 1 up to 10,000. The output will be a single integer representing the total number of valid combinations that satisfy these conditions. For example, if nums is 1, 2, 3, and the target is 4, the output would be 7. Here's why: the valid combinations are 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 2 plus 1, 1 plus 3, 2 plus 1 plus 1, 2 plus 2, and 3 plus 1. Notice that the order of the numbers matters, so 1, 2, 1 is different from 1, 1, 2. This is why all these combinations are counted as distinct. Now, consider a different case where nums is 9 and the target is 3. In this case, the output is 0 because the only number in the array, 9, is greater than the target, meaning no combinations are possible. These examples illustrate how the order of numbers and the range of possible values in nums play a critical role in determining the result. Another example highlights the scalability of the problem. Suppose nums is 1, 2, 3, and the target is 32. In this situation, the number of valid combinations is a very large number, 181,997,601. This shows that while the problem can involve significant computation for larger targets, the constraints ensure the solution will always fit within a 32-bit integer. It emphasizes the importance of an efficient algorithm, as brute forcing through all possible combinations would be infeasible for such high values of target. The input constraints, such as the maximum length of nums and the upper limit on target, ensure that the problem remains solvable within reasonable computational limits. To summarize the constraints, the length of nums can range from 1 to 200, and every number in nums is distinct and falls between 1 and 1000. The target is always a positive integer between 1 and 10,000, and the output is guaranteed to fit within a 32-bit integer. It's also important to note that since order matters, this problem is a variation of the classic knapsack problem, where you aim to determine the number of ways to achieve the target by combining the elements of nums in any order and allowing each element to be used repeatedly. This variation introduces the challenge of counting permutations rather than just combinations, making it a unique and interesting dynamic programming problem to solve. To tackle this problem, we initially considered two approaches. The first is the brute force method using recursive backtracking. Here, the intuition is to generate all possible combinations of numbers from the array nums that sum up to the target. We explore every path recursively, reducing the target at each step, and count the valid combinations once we reach the base case where the target equals 0. However, this approach has significant drawbacks. Since the same combinations can appear in different orders, we end up exploring many redundant paths. This makes the recursion tree grow exponentially, leading to very poor performance for larger inputs. The time complexity for this method is n-target, which is highly inefficient, and it also requires target space for the recursion stack. Recognizing these limitations, we then turn to an optimized approach using dynamic programming with a top-down memoization strategy. The idea here is to avoid recalculating results for the same subproblem by storing those results in a memoization table, effectively reducing redundant computations. For this, we use a DP array where dp, I, represents the number of ways to reach the target value I. By solving each subproblem only once, we can break down the problem into smaller, overlapping subproblems and dramatically improve efficiency. Memoization plays a crucial role in the top-down dynamic programming approach, as it ensures that each subproblem is solved only once. This optimization significantly reduces the time complexity to O, n asterisk target, where n is the size of the array nums. The space complexity is O, target, to store the DP array, along with the space used by the recursion stack. However, this approach still relies on recursion, so we also considered the bottom-up dynamic programming method, which eliminates recursion altogether. In this approach, we build the solution iteratively for all target values from 0 to the given target. We use a DP array where DP, I, is calculated by summing DP, eignumber, for all numbers number in nums, provided that eignumber is non-negative. The base case is straightforward, DP, 0, is initialized to 1, as there is exactly one way to achieve a target of 0, by using no numbers at all. For each subsequent target value, we compute DP, I, incrementally using this recurrence relation. This iterative method avoids recursion entirely, making it more memory efficient, and it ensures that we only compute results for reachable target values. With a time complexity of O, n asterisk target, and a space complexity of O, target, this approach is both efficient and practical for large inputs. Given the various approaches, we chose the bottom-up dynamic programming method as the preferred strategy for this problem. Both top-down and bottom-up dynamic programming approaches share the same time complexity of O, n asterisk target, and space complexity of O, target. However, the bottom-up approach avoids the recursion stack, making it more memory efficient. Additionally, its iterative nature simplifies implementation and debugging, reducing the chances of errors during coding. This approach is also more scalable, as it eliminates the risk of stack overflow errors that can occur with deep recursion when the target value is large. Comparing the options, the brute force method is clearly infeasible for large target values due to its exponential time complexity. The top-down dynamic programming approach is a significant improvement but still requires additional space for the recursion stack. In contrast, the bottom-up approach combines efficiency, simplicity, and scalability, making it the most practical and robust choice for solving this problem. The key insight, or aha moment, for this problem was recognizing that it could be framed as a classic dynamic programming problem involving the counting of combinations. This realization allowed us to leverage the problem's overlapping subproblems and optimal substructure properties. By iteratively building the solution for all possible target values, we were able to avoid redundant computations and recursion overhead. This structured approach not only simplifies the solution but also ensures that it is both efficient and scalable for a wide range of input sizes. This insight was instrumental in selecting and implementing the bottom-up dynamic programming strategy, which provides a clean and efficient way to solve the problem. To solve combination sum 4, we start by understanding the problem requirements. We are given an array of integers, nums, and a target value, target. The goal is to determine the number of unique combinations of numbers from nums that sum up to the target. Importantly, each number in nums can be used multiple times. A recursive backtracking approach is a natural fit for this problem because it allows us to systematically explore all possibilities. First, we define the base cases. If the target becomes 0, we know we've found a valid combination, so we increment our count. On the other hand, if the target drops below 0, the current path is invalid, and we backtrack immediately. Next, we handle the core of the recursion. For every number in nums, we subtract it from the current target and make a recursive call with this reduced target. This process explores all potential combinations by looping through nums and trying each number as part of the solution. The recursion stops when we either find a valid combination or the target becomes negative, ensuring that the algorithm terminates appropriately. Now, as we deepen the recursive exploration, we incorporate path tracking. We maintain a temporary list called current_path to keep track of the numbers included in the current combination. Before making a recursive call, we add the current number to this list, and after the call, we remove it. This backtracking step ensures that we undo changes and restore the state for exploring other paths. Additionally, since numbers can be reused in this problem, we do not exclude the current number from subsequent recursive calls. This means that a number can appear multiple times in a single combination. Finally, as we explore all valid paths, we aggregate the results by counting the total number of valid combinations. This count is the output of the algorithm, representing the number of unique ways to achieve the target sum. Backtracking is particularly well suited for this problem because it allows us to exhaustively explore all combinations while avoiding unnecessary computations. The idea is to explore a path and backtrack as soon as we determine that it cannot lead to a solution, which keeps the process efficient. One key optimization is pruning. By terminating recursion when the target becomes negative, we eliminate invalid paths early, reducing the size of the search space significantly. Another critical insight is handling duplicates. Since the problem allows reuse of numbers, we don't need to worry about exclusion. The recursive structure naturally manages this by ensuring that every number is reconsidered at each step. This approach guarantees that all valid combinations are explored without redundancy. To implement this algorithm, we rely on three main data structures. First, the array num stores the input numbers and is iterated over in each recursive step. Second, the list current underscore path keeps track of the combination of numbers being explored. This list is modified dynamically by adding and removing elements, which facilitates efficient backtracking. Lastly, we use an integer variable target to represent the remaining sum required to achieve the goal. This value is updated during each recursive call to reflect the reduced target. The key operations in this algorithm are the recursive calls and the backtracking steps. The recursive call explores new states by reducing the target and updating the current underscore path. Once a path has been fully explored, backtracking undoes the last operation, restoring the previous state and allowing the algorithm to explore other possibilities. Finally, let's analyze the complexity of this approach. The time complexity depends on the number of paths the algorithm explores. In the worst case, if target is large and the array nums contains n elements, the algorithm examines all possible combinations, leading to a time complexity of approximately n(target). This exponential growth reflects the exhaustive nature of backtracking. For space complexity, the primary constraint is the recursion stack, which grows with the depth of the recursive calls. Since the maximum depth corresponds to the target value, the space complexity is target. These complexities highlight the trade-off between a comprehensive search and computational efficiency, making this algorithm suitable for moderate-sized inputs. Here, we define a class called solution that contains a method named combinationSum4. This method takes two inputs, a list of numbers, nums, and an integer target. The goal is to determine the number of unique combinations that add up to the target using numbers from nums. To tackle this, we use dynamic programming with memoization. First, we initialize a memoization table, memo, with a size of target +1, and fill it with -1 to represent unknown states. This table will help us store results for subproblems, avoiding redundant calculations. Next, we define an inner helper function called dp that takes the remaining target as an argument. If the remaining value is 0, it means we've found a valid combination, so we return 1. If the remaining value is negative, it means the current combination is invalid, and we return 0. If we've already computed the result for this remaining value, we simply return the cached result from the memo table. Otherwise, we calculate the total number of combinations recursively by iterating through each number in nums and subtracting it from the remaining value. The results of these recursive calls are summed up to give the total combinations for the current state. Finally, we store this result in the memo table to save it for future use and then return it. At the end of the method, we initiate the recursion by calling the dp helper function with the full target value as its argument. This kicks off the process of breaking down the problem into smaller subproblems, leveraging memoization to optimize the computation. By the time the recursion completes, dp target will have computed the total number of unique combinations that sum up to the target using the numbers in nums. This final result is then returned as the output of the combinationSum4 method. Here, we begin by defining a Java solution for the combinationSum4 problem. The main function, combinationSum4, takes two inputs, an array of integers, nums, and a target value. We initialize a memoization array, memo, which will help store the results of subproblems to optimize our recursive approach. The array is filled with -1 to indicate that no subproblem has been resolved yet. This ensures we only compute each subproblem once, avoiding redundant calculations. The core logic is handled by a helper function, dp, which is called with the nums array, the target, and the memo array. Within the DP function, we first handle the base cases. If the remaining value is 0, it means we've found a valid combination, so we return 1. On the other hand, if the remaining value becomes negative, no combination is possible, and we return 0. Lastly, if the result for the current remaining value is already computed and stored in the memo array, we simply return that value to save computation time. Now, we calculate the total number of combinations for the current remaining value. To do this, we iterate through each number in the nums array. For every number, we recursively call the DP function, reducing the remaining value by that number. The results from these recursive calls are added to the total combinations variable, which keeps track of the total number of valid combinations for the current state. Once the total is computed, we store it in the memoization array at the index corresponding to the current remaining value. This ensures that if we encounter the same remaining value again, we can retrieve the result directly from the memo array instead of recalculating it. Finally, we return the total combinations value, which represents the number of ways to achieve the target using the given numbers. To solve combination sum 4, let's walk through the first example with nums equal to 1, 2, 3, and target equal to 4. We start by initializing our memoization array, which is sized to target +1 and filled with -1 to indicate that no values have been computed yet. At the core of our solution is the recursive function DP, which calculates the number of combinations for a given remaining target. Starting with DP, 4, we initialize total underscore combinations to 0. For each number in nums, we subtract it from the remaining target and make a recursive call. For instance, when number is 1, we call DP 3, when number is 2, we call DP 2, and when number is 3, we call DP 1. Now, focusing on DP 3, the process is similar. We initialize total underscore combinations to 0, iterate over nums, and make recursive calls. For number equal to 1, we call DP 2, for number equal to 2, we call DP 1, and for number equal to 3, we reach DP 0. The base case is critical here. DP 0 equals 1 because there's exactly one way to form a target of 0, by using no numbers at all. This value propagates back up through the recursion. As we continue resolving DP 3, the results of the recursive calls are summed up, and we store the result in memo 3, which is 4. This caching prevents redundant calculations in future recursive calls. Similarly, we compute DP 2 and DP 1 using the same recursive approach, leveraging memoization wherever possible to optimize performance. Finally, for DP 4, the total combinations are calculated as 7, which becomes our final output for this example. This means there are 7 distinct ways to form the target 4 using the numbers 1, 2, 3. Moving to the second example, nums is now 2, 3, 5, and the target is 8. Again, we initialize the memoization array with -1. Starting with DP 8, we iterate over nums and make recursive calls for DP 6, DP 5, and DP 3, subtracting each number from the current target. Next, for DP 6, we repeat the recursive process using nums to compute the combinations for this subproblem. Throughout this process, we store intermediate results in the memo array to avoid recomputation. This memoization step is crucial for improving efficiency, especially as the problem scales to larger targets or arrays. Ultimately, for DP 8, we sum up all the valid combinations from the recursive calls, and the result is 10 distinct combinations. For the final example, nums is 1, and the target is 10. Here, the memo array is initialized with a size of 11, and each recursive call reduces the remaining target by 1. With nums containing only the number 1, the solution is straightforward. The only way to form any target is by repeatedly adding 1. For DP 10, we calculate sequentially from DP 1 to DP 10, with each step building on the result of the previous one. The base case, DP 0 equals 1, ensures correctness, and the final result for DP 10 is simply one combination. This demonstrates the simplicity of the problem when nums contains just one number. To analyze the time complexity of the combination sum4 function, we start by examining the recursive calls. The function DP, remaining, calculates the number of combinations for each value of remaining between 0 and the target. For each remaining value, the function iterates through all elements in the nums array. If nums has n elements, this results in up to n recursive calls for every remaining value. Since we use memoization, each unique remaining value is computed only once and stored in the memo table. This ensures that the total number of recursive calls does not exceed target plus 1, which corresponds to all possible remaining values. Considering the loop over nums in each recursive call, the time complexity per unique remaining value becomes O, n, dot. Now, looking at the overall time complexity, we know there are O, target, unique remaining values, and for each of these values, the function performs O, n, work by iterating over the nums array. This gives a total time complexity of O, target, asterisk O, n, which simplifies to O, target asterisk n. Shifting to space complexity, the memo table stores results for all remaining values from 0 to target, requiring O, target, space. Additionally, the recursion stack depth depends on the maximum remaining value, which can also reach up to target in the worst case. Therefore, the total space complexity combines the space used by the memoization table and the recursion stack, resulting in O, target, plus O, target, or simply O, target, dot. When we compare this approach to a naive method, the difference becomes clear. A brute force solution would involve generating all possible combinations of numbers and nums to reach the target, which has an exponential time complexity of O, n caret target, due to the sheer number of subsets being explored. In contrast, the optimized approach using memoization ensures that each state is computed only once, significantly reducing redundant calculations. This optimization brings the complexity down to O, target asterisk n, making the solution far more efficient and scalable for larger inputs. Considering best, average, and worst case scenarios, we see that in the best case, if all numbers in nums are greater than the target, the function quickly determines that no combinations are possible. However, even in this case, the memoization table still needs to be initialized, so the complexity remains O, target, dot. In both the average and worst cases, valid combinations exist, and all numbers in nums can contribute to these combinations. Here, memoization ensures that each state is computed only once, maintaining the time complexity at O, target asterisk n. Mathematically, this is because the total number of recursive calls corresponds to the number of states, or target plus 1, and the work per state is proportional to n. By avoiding redundant computations, memoization prevents exponential growth, resulting in a time complexity of O, target asterisk n, and a space complexity of O, target. This efficient design highlights the significant improvement over the naive approach, which has an exponential complexity of O, n caret target. One common mistake in problems like combination sum 4 is failing to handle duplicates in the input. If the array contains duplicate numbers and you don't account for them, you might either generate duplicate solutions or miss unique combinations entirely. This is especially problematic in cases where the solutions must have distinct subsets. To avoid this, a good practice is to sort the input array first and skip over duplicate elements during your recursion or iteration. Another issue is not pruning the search space in recursive solutions. Continuing to explore paths that exceed the target wastes computational resources and unnecessarily deepens the recursion stack. A simple fix is to add a condition to terminate recursion early when the current sum goes beyond the target. Lastly, improper base case handling is a frequent pitfall. Without a correct base case, your recursion might loop infinitely or produce incorrect results. Always ensure the base case checks if the target has been met and adds valid solutions appropriately. Another common issue involves incorrect index handling during recursion. This often happens when solving combination-type problems where the starting index plays a critical role. For example, if you fail to move the index forward, you might end up repeating results or missing valid solutions. It's important to understand whether the problem allows for reusing elements, as in permutations, or prohibits reuse, as in combinations, and adjust the starting index accordingly. Additionally, ignoring edge cases is a frequent oversight. Scenarios like an empty input array, a target of 0, or negative numbers in the input can cause runtime errors or produce unintended behavior. To handle this properly, you should explicitly check for and address these edge cases before diving into the main logic of your solution. When approaching problems like combination sum 4 in interviews, recognizing patterns early can give you an edge. Many problems involving subsets, combinations, or partitions share common approaches, such as backtracking, dynamic programming, or even a hybrid of both. Identifying whether the problem fits into one of these categories can guide you toward the most efficient solution. Interviewers often ask about time complexity, so it's crucial to understand the worst-case scenario for recursive solutions, which often have exponential complexity, like O(2 to the power of n). Be prepared to discuss ways to optimize these solutions. It's also worth noting the trade-offs between recursive and iterative approaches. Recursion is generally easier to write and understand, but it risks stack overflow with large inputs. Iterative or dynamic programming solutions avoid this but are often more challenging to implement. Lastly, always consider space complexity, including both recursion stack space and any auxiliary data structures your approach uses, and be ready to explain those trade-offs. Combination Sum 4 has strong connections to other problems that can deepen your understanding of this pattern. For instance, in combination sum, problem 39, you need to find all unique combinations in a candidate array that sum to a target, and recursion with pruning is a key strategy there. Combination sum 2, problem 40, is similar, but the input can include duplicates, and each number can be used only once per combination, making duplicate handling critical. Partition equals subset sum, problem 416, involves deciding if an array can be split into two subsets with equal sums and is often solved using dynamic programming techniques. Finally, subsets 2, problem 90, asks for all unique subsets of a list that may contain duplicates. This requires careful handling of duplicates to ensure that no subset is repeated. These related problems highlight how similar concepts, like recursion, pruning, and duplicate handling, recur across different variations. There are also alternative approaches to solving problems like combination sum 4, each with its own trade-offs. Dynamic programming is one powerful method. While it is more efficient in time and space compared to backtracking for problems like subset sums, it can be more challenging to implement and debug. For example, partition equals subset sum, problem 416, is a classic scenario where dynamic programming shines. Another option is iterative combinatorial generation, which avoids recursion altogether. While this can be useful for tasks like generating power sets or combinations, the implementation can become cumbersome and less intuitive. Finally, memoization in recursive solutions is a highly effective optimization technique. By storing results of overlapping subproblems, you can prevent redundant computations and significantly reduce time complexity. However, this approach requires additional memory to maintain the memoization table, which adds to the space complexity. Each of these approaches has its strengths, and understanding their trade-offs is key to choosing the right one for a given problem. Great work completing this walkthrough. We reviewed the problem, discussed the brute force approach using recursive backtracking, and highlighted key insights. Remember to practice similar problems to deepen your understanding. Thank you for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!